Okay, so water, H2O obviously, we did the molecule. Okay, so there's the easy equivalent of oxygen, 2 lone pairs, 2 sticks. All I'm going to do, stick a hydrogen on the end of each stick. And yeah, there it is. Okay, so there it is. I've got my 2 hydrogens, 2 sticks, oxygen, and then 2 lone pairs. All right. Methane, interesting. Let's take a look at methane. So methane, carbon should look like that. Hydrogen should look like that, right? So obviously carbon in the middle, and then there's 4 hydrogens. Just hook them up. Hook them up. There it is. How many electrons? 2, 4, 6, 8. 8's a popular number because remember we need 8 electrons to get that full layer. All right. What would that look like? Well, it's a 3-dimensional shape. It's a tripod, right? So those bonds are at these kind of tripod angles, which is 109 degrees. More on that in the next packet. Okay. So in the next packet, we'll talk more about true molecular shape. Well, we wouldn't call it a tripod, right? We'd call it a tetrahedron, right, for reasons to talk about. But there it is. Okay, so there's my tripodish methane, CH4. Every carbon, well, the carbon has 4 sticks, the hydrogen has 1. It obeys the rules of valency, we call it. All right, now the next one, phosphorus. If we look at phosphorus in the periodic table, it's actually right under nitrogen, right? So it's going to have those 5 outside electrons. And then remember, if we do EZ, those singles turn into hands that need to be held. Now be careful, I said chlorine is going to be lots of electrons, right? Because chlorine has 1, 2, 3, 4, 5, 6, 7, right? So it makes 1 bond and then 6, all right? Now if I think about it, chlorine by far has the more electrons, but this has a higher valency, so I put it in the middle and copy over all those electrons. Then we just put the chlorines around it, and they're still there, those electrons, so be careful, be careful. Right, have it hold hands, have it hold hands, have it hold hands. Ah, there it is, right? So if I do that one, oh, again, I'll use a blue because, actually I'll disassemble my ammonia over here. So phosphorus acts just like nitrogen, right? So pretend the blue one's phosphorus. Then I'm just going to stick chlorines on the end. Chlorines are traditionally green, as we mentioned, right? So there we go. Now often in class, someone will show me that and I say, oh, is that right, Dr. Mills? Well, no. You got the framework, but you don't have all those extra electrons, right? So lots of paddles. It's very busy, all right? Paddles are getting a bit scarce here. I have to cannibalize some other ones. There we go. Kind of looks hectic, right? But there it is. So there's my center of phosphorus. Let's put it like this. That's better, right? If I hold it like this, you can see it better. So there's the center of phosphorus with its lone pair. That's here, okay? And then we have the 3 chlorines surrounding it, which are the green ones. Each have 3 lone pairs themselves. So pretty busy, but there it is, okay? Now here we've got to count the electrons. Oh, it's kind of a nightmare to count all these dots and lines and things, right? But there's an easier way to do it. And this kind of reminds me of going to college myself, okay? You know what it's like, and I'm talking to everybody who's over 21, right? So you go to a student party and you bring your drink with you, right? And because, you know, as students, we've got no money, and when you get to the party, you don't want anybody drinking your beer. So what do? You hide your beer somewhere in the room, right? My favorite was to hide my beer in the dishwasher, because no one looks in the dishwasher. If you're kind of a naive person, you'd hide your beer in the fridge, and everybody will take your beer if you do that. Do not hide your beer in the fridge, okay? So when it gets down to it, and you've got to kind of figure out well, say you're the host of the party. Well, how many electrons do I have? How many beers do I have at my party? You've got to kind of look around the room, look under the coats, look in the dishwasher, and you'd find eventually all the beers. But it's kind of hard to look around the room and look around the molecule and find all the dots, find all the beers, right? But what would be a simpler way, right? As people came in the door of your party, you just ask them, hey, how many beers did you bring? If you do that with an atom, you say, hey, how many electrons did you bring? Phosphorus, it's valence electrons we're talking about, right? Those are the ones that do the work. Phosphorus is in column 5, so it brings 5 electrons, right? So phosphorus brings 5. Chlorine's in column 7, so it brings 7. So that brings 5, that brings 7, that brings 7, that brings 7. So it's 5 plus 7 plus 7 plus 7, 21, and 5 is 26 electrons. So you just count the beers as they come through the door, all right? Then you don't have to count around the room. But we can try and do it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So yeah, it is 26, but it's kind of hard to see them, okay? All right. Next thing. Now, oftentimes, and we kind of mentioned it up here a little bit, okay, there are things called multiple bonds, double bonds and triple bonds. A double bond just means 2 sticks between 2 atoms. A triple bond is 3 sticks, okay? Now, I tell you this story to kind of help with your education, but it is kind of a bit of a one of those, you know, kind of flashback things from the past, which kind of wakes you up in a cold sweat once in a while, okay? Now, as you may know, I went to school in England, okay, and when I went to kind of what's called primary school, which is like kindergarten essentially, right, or, you know, junior school, okay, you have that one teacher who teaches you everything, and we had Mrs. White, who was Scottish, right, she's like the Highlander, right? She's like some Highland warrior, right, so she's really scary when you're 9 years old, okay, and Mrs. White used to teach us everything, English, math, everything, right? Including physical education, all right? Now, when Mrs. White was teaching us physical education, we didn't go out and play games like soccer or tennis or anything like that. Oh, no, no, no. Mrs. White took it upon herself to teach us Scottish country dancing. Okay, now, I don't know if you're familiar with Scottish country dancing. It should be classified as a martial art, right? It's pretty kind of rough and ready kind of dancing. And here they are, dancing around, right? Okay, now, how does Scottish country dancing work? Well, it kind of works like this, okay? So you basically have 2 people, and I draw it here. All right, so here's me as a wee lad, right? So there's me, 9 years old. And here's my dancing partner. And to make it worse, when you're 9, you have to dance with these things called girls, right? Here she is, Nicola Guy, I remember her name. She scared the crap out of me. She's much bigger and scary, right? And what happens is, you basically hold hands with your partner, but you have to grab them twice. So you grab hold with both arms, right? So this is a consequence of having 2 bonds, having 2 arms if you're oxygen, and only 1 partner to go to, right? So if you have more bonds than you have partners, you just make more bonds, right? So there we are, right? So we form what we call a double bond, yeah. Now this is where it gets scary because at this point, Nicola Guy, who's much bigger than me and much stronger than me, grabs me and starts to swing me around like a giant hammer in the Olympics, right? And this is what has caused me trauma. Right? I tried looking Nicola Guy up on the internet. I can't find her. My guess is she's in jail. I'm joking. All right. Now, why does this remind me of oxygen? Remember, all you do with atoms is you have them hold hands. So I'm going to have them face each other, right? And the oxygen EZ, remember, looks like that, right? So there they are. All I'm going to do is basically have them hold hands. Now, when we do it for real, we'll do a straight line between the 2, but I'm just going to show you how that works, okay? Have them hold hands. There, so I've got 1 partner and 2 bonds to make. Oxygen makes 2 bonds always. It's got 2 sticks. Does that look like it's easy? Yes, it does. It's got 2 sticks, 2 lone pairs. Now, when we do this with a model, it's kind of weird, right? So let me show you 2 oxygens real quick. So I have my 2 sticks, and well, how can I make them both go to the same place? It's kind of impossible if they're straight sticks like that. I can't make them both go to the same place. Then we go to the legend of the bendy stick. Okay, so in our modeling kits, we have these bendy sticks, which allow you to kind of crank over your bonds and make them go in the same direction. Okay, so bendy sticks are only used for multiple bonds. We can use 2 or 3. Okay, there it is. So that is what oxygen looks like as a model. I've got my 2 sticks. Each oxygen has 2 sticks and 2 lone pairs, like it's easy, but they both go to the same place. Turns out that multiple bonds are simply a consequence of less neighbors than sticks. Okay, so you've got more sticks, they've got to go somewhere. They're a bond, remember. You can't have a stick going nowhere. It's got to go somewhere. It goes to its neighbor. Now, because we have a double bond here, this messes up our rule of 8s a little bit. So how many electrons? 2, 4, 6, 8, 10, 12 electrons. Makes sense. Oxygen brings 6, column 6. 2 6 to the 12. All right, pause there. Try nitrogen. Nitrogen has a triple bond. That's a clue, right? So nitrogen makes 3 bonds and it's N2, so I'm going to have 3, right? And then hey, and we'll see why later. Got to make each nitrogen look like it's easy, so it has that extra lone pair. There it is. Okay. If I do a model for that, I'm going to have to use the 3 bendy sticks, right? Got to crank on it a little bit, and here I am on the side doing this. Now, if we did this in class, it's kind of a tricky one, but we can just about crank them over and get them in there. Oh, I'm having a problem. Yeah, I'll hold it just to show you it works. Yep. All right, so you get the idea. Okay, this goes in here. And then this goes in there. Okay. I think my nitrogen's a little dodgy here. Hang on. Yeah, it's not going to go. Basically, you have, I'll put it on the page so you can see it. That last one kind of cranks over and goes. Oh, just about got it. Goes in there. Okay, so that's a triple bond, we call that. So 3 sticks from one place to another between 2 atoms is a triple bond. Okay, that's what we got there. Now it kind of makes sense to kind of make it symmetric like that, and we'll see why in the next packet. But look at it. Does it look like it's easy? Well, yeah, I mean, it doesn't matter that the sticks will go in the same direction. It's 3 sticks, 1 lone pair. I just had them hold hands, okay? So 2 nitrogens, N2, back to back, has a valency of 3, makes 3 bonds. Okay, triple bond. That's called a triple bond. That was called a double bond. If I did it correctly, that's the Lewis for oxygen, Lewis structure. That's the Lewis for nitrogen. That's a triple. That's a double. All right. Okay. How many electrons? Well, column 5, 2 5s are 10. 2, 4, 6, 8, 10. Okay, remember each line in each lone pair is 2 electrons. All right. Finish it up. Okay, hydrogen fluoride. H looks like that. Fluorine, column 7, looks like that. Just have them hold hands. HF, 7 and 1 is 8 electrons. Finally, this one should be easy because we've already done water, right? If you think about it, sulfur and oxygen are in column 6. They both have the same EZs. So I'm just going to swap out sulfur for oxygen in the Julie Andrews molecule, right? 2, 4, 6, 8 electrons in the valence. All right, there you go. Now, to be honest, this is kind of a MacGyvering technique, right? So you can do this, you know, just by obeying the rules of valency. If you have that kind of easy kind of cheat sheet, we'll call it, right? So as long as you kind of remember, hey, you know, each single electron becomes a hand that needs to be held, then just have them hold hands, you will always get the simple molecule nice and easy. Okay, works for double bonds, triple bonds, every kind of bond. All right, but sometimes it's just not obvious, okay? And we have to kind of default to the rules, all right? So maybe if you didn't like what we just did and you want some kind of instruction set that works every single time, you can certainly do that, okay? And this is what we're going to do right now, all right? So the rules will work for everything, okay? The rules will work for everything. And they're empirical, just like we did the points of a compass. There's a lot of empirical stuff with Lewis structures, okay? One that's kind of right on the line between being able to MacGyver, you know, just kind of use the rules of valency, and then using the rules is CO2. Okay, but this does work for more complex things. So the weirder it gets, and we'll do this one later, we can actually do molecular ions. How on earth will we model 2 extra electrons? Well, we can't do it with our kind of simple EZs, right? But we can do it with the rules, all right? So we use the rules for something that's kind of in-betweeny, if you like, CO2, and then we use the rules for the harder ones. So if you ever got a molecular ion of some sort, you always use the rules, all right? Now, the great thing about the rules is it works for everything. So even the simple ones, if you want to practice the rules, go back, try water or something, right? Okay, but we'll do carbon dioxide first, all right? Now, first thing to do, we're going to do CO2, all right? What we're going to do is just figure out essentially how many valence electrons we're going to sprinkle over this stuff, right? So carbon brings 4 valence electrons, and oxygen brings column 6, right? 6. And there's another oxygen, right? So 4 plus 6 plus 6 equals 16, right? 16 electrons. And that's a multiple of 8, which makes sense because, hey, 4 layer is 8, right? Now, the power of this theory is that, hey, when you use those, well, when you try and model those molecular ions, if I had something like CO3 2-, that actually has 2 extra electrons that came in from the outside. So we just add 1 electron per negative charge, because electrons are negative, to our count, right? So we'd add 2 for CO3 2-. If it was something like ammonium, which is a +1, we'd actually take 1 away. So we can modify our count after the fact to say, hey, electrons have been added or lost, right? But hey, this one, just a molecule, neutral, 16 electrons. All right, so for CO2, 16 electrons to sprinkle. Now, similarly, what we're going to do, like we did with the Julie Andrews molecule, we said, hey, Julie goes in the center because she has the most sticks, right? She's like the hub of the wheel, and that's true for this model too. So whatever's got the most sticks, the highest valency will go in the center. And the same rules will generally apply, right? So the atoms are going to look like their EZs, right? So which one goes in the center? Well, it's going to be carbon. It's got the most 6. And just, you know, symmetrically, and we'll see why we do this in this way later, but it just makes sense to kind of spread them out in a symmetric way, right? So put the highest valency, carbon will make 4 sticks. It's like the hub of the wheel, has the most spokes, so it makes sense to go at the center. And then oxygen around it. Okay, so write the atoms on the page with the highest valency atom in the center, and then just put things either side. So it's very similar to what we did with Julie Andrews, right, with the water molecule. Now, minimally, the atoms have to be connected for a molecule to exist. Okay, these are just atoms floating there in space right now. So minimally, I have to have 1 stick from the inside to the outside, minimally, right? So hey, that's our first thing. Connect the outer atoms to the center with a single line, which is a shared pair of electrons, right? All right, empirical rule, we just follow the rules. It works at the end, okay? So now we've got this framework. We have to sprinkle 16 electrons over this framework. We've already put in 2, which is a shared pair, and 2, which is a pair. So we put 4 in, we've got 12 to go if you like, okay? So next, complete the valence shells of the outside atoms. Now remember, oxygen, when it's stable, requires 8 electrons. Just think about where an atom is in the periodic table, okay? Oxygen's in row 2, so to have a full layer, it will have 8. It will look like neon, right? That's already 2, isn't it? So it needs to be stable. Remember, all atoms are stable when bonded, right? It needs 6 more. And that's what we're going to do. Electrons travel in pairs, always bonded or lone, okay? So we're going to complete the valence shells of the outside atoms to give them full layers, right? So 2 is a shared pair. Remember, they both own it. So 2, 4, 6, 8. That's now happy. It's stable, right? It's got 8 electrons. Do the same over here. 2, 4, 6, 8. Happy. There we go. All right. So, you know, we're kind of getting there. we've completed the outside atoms. They've got 8 electrons and 8 electrons. All right. Now, you may be saying to yourself, well, what about poor old carbon in the middle? Is carbon stable? Does it have 8 electrons? No, it has 2, 4, right? So carbon's definitely a bit cranky right now. So it's not done. It's not done, right? So the trick, we'll keep going. Next rule, all right, I'll keep the picture there. Can I pull the electrons from the structure and compare it to the number needed, right? So we need 16, all right? Nope. We need 16, all right? But right now, we only have 2, 4, 6, 8. Well, let's count them, right? I didn't say only. Let's count them, right? So compare to the number you need. We got 16. How many we got? 2, 4, 6, 8, 10, 12, 4. Oh, we do have the right number. All right. We do have the right number. We do have 16. Okay. Now, in rare occasions where we didn't meet it, so say we got to 15, right? We put extra ones on the center, right, to make the number right. Okay. And that's a very rare example we'll show you later. Okay, but typically this is the right answer. Okay, it's normally, we very rarely apply rule 5, but just double check you got the right number. 16, 16, good to go. But as you can see, it doesn't look anything like it should. Carbon needs to have 4 sticks, it's only got 2. Oxygen needs 2 sticks and 2 lone pairs. Well, it's got the right number of electrons, but they're all messed up, right? Okay, now, here's the thing. Number 6, this is the big rule here, okay? We're going to do some conversions. We've got the right number of electrons, they just happen to be in the wrong spot, okay? So all we're going to do is convert owned pairs into shared pairs. Kind of reminds me of a story. Now, you will relate to this story if you have a younger brother or sister, okay? So when I was in graduate school, I used to go home to England for Christmas and things, and I'd meet my brother, who's a couple of years younger. Okay, and he'd say to me, hey, do you want to go down to the pub? And I'm like, oh, pub, that's where they keep the beer. Yeah, sure. And so then he'd have this brilliant idea. Hey, let's all put some money in this hat, and then when we get down to the pub, we'll use it to buy the beer. So I'm like, okay. So I put the money in the hat. Okay, so what does that mean? So these electrons, these lone pairs, are actually owned by this atom, aren't they? This is money in my pocket. This is me, this is my brother, right? So he says, oh, let's share the electrons. So my money becomes our money. I turn an owned pair into a shared pair. Did I change the number of electrons? No, I did not, right? I just gave a double bond, right? So a double bond is just turning an owned pair into a shared pair. That makes him happier, right? Am I happy? Well, kind of. I'm happy that you're happy because look, I look exactly like I should now. I've got 2 sticks and 2 lone pairs. I look like my EZ. So I'm fantastic, all right? Is he happy? Well, he's better. He's not perfect because, hey, carbon needs what? 4 sticks, right? It's got 3 sticks. Can I give him another stick? No, because I can't make 3 bonds. I can only make 2. Ah, let me introduce you to Gary over here. Right? Gary, we're going down the pub. Put some money in the hat. Okay. There we go, right? So now everybody has the right valency. So that's the trick. If you get to the point where the structure doesn't look right, carbon needs 4 sticks, oxygen needs 2, just turn owned into shared and we're good, okay? So there's the final answer. Double check the valencies, carbon 4 sticks, oxygen 2, they all look like they're EZs, don't they? Okay, oxygen has 2 sticks and 2 lone pairs, carbon has 4 sticks. All right, now, pause here, right? I'm going to ask you to try the first 2, okay? And this one takes a little bit more explaining, which I'll probably do in the next video, okay? So pause, try them, okay. First one, CHCl3. Now of those, carbon has the highest valency. Stick it in the middle, all right? If you follow the rules through, you'll get the same answer, okay? But you can MacGyver this one. You can just follow the rules of valency like we saw before, okay? And you'll get that. Make sure you can see that. There we go. That's the right answer. Okay. Next one. That's all single bonds. That's why it's easier. Next one has a double, right? So let's just do this one, if you like, for real. So CH2O. Follow the rules. How many valence electrons? Carbon brings 4. Hydrogen brings 1, and there's 2 of them. And oxygen brings 6. That's 12 electrons, right? So I've got 12 electrons to sprinkle over my structure, right? Who goes in the middle? Well, who has the highest valency? Well, carbon is going to have 4 sticks, hydrogen 1, oxygen 2 sticks, 2 lone pairs, right? Okay, so carbon goes in the middle. All right, spread the others around it. Oh, hydrogen. Got that hydrogen. Okay, CH2O. All right, so that's our framework. One with the most sticks in the middle. Others surround it, right? Connect the inside to the outside. Boom. Complete the outer octets. Just like above, oxygen needs 8, it's in row 2. Hydrogen, if you think about it, is in row 1, so it's already got its 2 electrons here. So hydrogen's, you know, it's basically decorative. There's no extra electrons on it because it's row 1, right? All right, there you go. Now, is it right? Well, no, because oxygen needs 2 sticks and carbon needs 4. Hydrogen's okay, though. Right, so now what we're going to do now, count up. 2, 4, 6, 8, 10, 12. 12 electrons, we're good. All right, but they're not arranged correctly. What do? Go down the pub. There it is. Okay. So final answer. This is probably how you see it in the book. There. Okay. Final answer. Now, I'm going to start this next one in the next packet because it's going to take more than 3 minutes to do it. Okay. Carbonate. I'll give you a head start though. Carbonate, and do it on a kind of a separate piece of paper. CO3 2 minus. Let's count the number of electrons. Okay, so carbon has 4, oxygen has 6, and there's 3 of them, plus the extra 2. Now that's where it's different, right? Plus 2 electrons from the outside because it's got 2 extra from it because it's made an ion, right? 18, 20, 24. I got 24 electrons to sprinkle over this structure. Okay, so try it. Carbon will go in the middle, oxygen around it. Start sprinkling, okay, and see how far you get. Now follow the rules explicitly and you'll get an answer. It will not look right, but it's as far as the rules take you, right? And then when you get that answer, we'll talk about how it's actually correct, okay? So if you can do this one, fantastic. Just get as far as you can and we'll pick it up again in the next video. Okay, stop there.